So far, it looks like exactly the same talk. Right? All right, now I'm standing between you and beer, probably. So you heard about me this morning. I'm still the same guy, only I've been to Troopers again. So for those of you who forgot, I used to be a software security person. And I retired when we sold Cigital. And since retirement, I started looking at machine learning stuff. Because I did machine learning work as a graduate student in Indiana University. I actually have a PhD in computer science and cognitive science. And I did a bunch of building of neural networks and case-based reasoning systems and genetic algorithms and Doug Hofstadter's models. I wrote a program called Letter Spirit, if you know the old AI stuff, back in the day. I heard all this hype about how AIs make huge, gigantic strides, and you can now, this machine understands this, and all sorts of other just absolute crazy nonsense. And so I was wondering, gosh, did we really make that much progress in 25 years that now machines understand stuff? They can read and talk? Really? So we started reading science papers, and of course they can't do any of that stuff. But what I found out reading these science papers is that pretty much everything that we built back in 89 to 95, all that stuff, the early connectionist stuff, if you focus on that, is still the same stuff that we're using. We're still using back propagation, we're still using gradient descent. There have been some major changes in the world that made those approaches better. And those major changes are computers are way faster and way bigger, number one. And number two, data sets are gigantic, enormous. So if you put ridiculously large numbers of cycles and huge data piles together and throw them at the old models, except for now we're just going to make them way, way bigger, so we're talking millions of nodes instead of 27 or whatever we had in the 80s. Then, that's where the progress has come from. So what accounts for the progress is faster computers and bigger data sets, but not really algorithmically all that much. That's not completely true, but that's kind of a general thing. Now, the thing is, during all of this, leap forward in convolutional neural networks, what we found is that not many people are paying attention to security. There are some, but they're not many, and they're not enough. And it's important that at this stage of the game, when we're talking about DNNs or machine learning of any sort, we need to think about security, and we need to think about security risks of the machine learning stuff itself. So that's what I'm going to talk about today. This is work that I've done in my tiny little institute called BIML. BIML stands for Berryville Institute of Machine Learning. And what's funny about that is Berryville is a tiny town of 5,000 people and some cows. And so you think of this tiny speck of a not really a city, a town in the middle of nowhere in Virginia, surrounded by cows, and we're doing some machine learning work there. And so, as tipping our hat to that dot in the middle of that cow is actually the shape of my county. So, and Berryville's right in the middle of the dot. So there's some symbolism in the cow. Anyway, it's kind of fun to have an institute in Berryville because, if Santa Fe can have Santa Fe Institute, then Berryville can have Berryville Institute. Which is pretty fun. And I have some sort of sad news. I have to go back to Virginia tomorrow morning. But the reason I have to go back is because my people in my town, all of the people I live with, normal people, asked me if I would please give them a talk on this stuff I was working on. What is machine learning, they say? What is it that you do? And I promised I would give them a talk in the community on July the 1st, and that's Friday. So I have to fly tomorrow and go give those guys basically the talk I'm going to give you right now. Except for normal people. It's way easier to give it for you guys, believe me. Right, so let's start with an introduction that's like 10 million feet. So who has not programmed in here? Everybody. Remember when you write your program and you thought you had everything done except for you forgot that one thing and you had to change the while condition or the if loop or whatever, or the until, and you had to keep on adding new stuff because you thought of most everything but not all the edge cases. Programming a computer is telling a computer how to do something very specifically according to an algorithm that you're writing. You're creating the algorithm yourself, and you're writing a computer program to carry that out. So programs specify how a task should be completed exactly. You can describe, look for 3 intersecting line segments. We're trying to identify triangles, and of course we could get really complicated and get down to the pixel level. But we could write a program to define triangles. That wouldn't be very hard. There are some things that we cannot describe the how for, though. Is that an English sentence? Well, there are infinitely many of those. And it turns out to be harder than you think to ask something like that. And so what we've done in machine learning is say, since we can't completely and fully specify how, we're going to talk about what. So back to our triangle, we say, that's a triangle, not a triangle, not a triangle, triangle, not a triangle, not a triangle, triangle, triangle. And we point at examples 1,000,000 times, or 1,000,000,000,000 times. Some of these machine learning models that I'm going to talk about later are huge, like GPT-3, which I'm sure you've heard about, from OpenAI, cost $12.5 million to build. For computational cycles, mostly, it was just cycles cost that much. Can you imagine? You know how cheap AWS cycles are, right? Imagine $12 million worth of those. Whew. And it had literally millions of nodes and billions of examples. And what we're doing when we do the what way is we just, we present an input-output pair, and if the machine gets it wrong, we adjust the machine and make it so that it gets closer to the right output that we wanted before. That's how backpropagation works. Does that make sense to everybody? So we're very slowly adjusting all of these parameters. There's many ways to do that. There are the connections, there's the thresholding function of the neurons, there's all sorts of stuff. And we do those minor adjustments millions of times, and we end up with something that is an auto-associative, sometimes predictive generator, because it's just an IO pair generator. Does that make sense to everyone? So, does GPT-3 understand language? No. It knows when it sees this string, usually that's the next string. And by string, I mean a whole bunch of bits with no meaning. It's just statistical associations. But with millions or billions of these associations, you can get some surprisingly complicated behavior that sort of begins to seem intelligent if you squint and say, clever Hans, bang your foot on the floor. So, a little bit more about AI. Some people say AI today, especially the press, artificial intelligence, and they mean machine learning. But there's a lot more to artificial intelligence than just machine learning. And there's a lot more to machine learning than just DNNs, neural networks, big neural networks, deep learning. So in the 50s to about the 80s, the space looked like this. And this is a slide I stole from Melanie Mitchell, who wrote this great book called Artificial Intelligence, A Guide for Thinking Humans, which is very skeptical. It has a very skeptical view of AI, a very much realistic computer science-based view of what we're actually building and whether we're actually making any progress towards general AI. Melanie doesn't really think so, and I agree with her. She was also a student of Doug Hofstadter's, by the way, like me. So AI, back in the McCarthy days in 1956, when they had the famous thing at Princeton where they said, hey, that would be cool to build some artificial intelligence. How long do you guys think it'll take? And they agreed collectively that it would take at least 2 weeks. Really? I'm not kidding. Yeah, that's good. Okay, a couple weeks we should be able to do that. Really? That's what they thought. It's been a while. We still don't have general AI. But remember, things that started out as AI, like how do I search for something, are now just search. Once we know how to solve them, they're not really counted as AI anymore, which is sort of the bane of AI's existence in computer science, but that's the way things go. So there was some machine learning, especially Bayesian analysis and things like that. And then things shifted around between 1990 and 2000, and machine learning got bigger, but deep learning was still pretty little. We had the invention of backpropagation by Rumelhart and McClellan. And basically, there had been a lot of good work on neural network stuff in the early days, up to like 1959, when Minsky and Papert wrote this book called Perceptrons. And the problem was that everyone was using two-layer associative nets. They didn't have a middle layer, so there was no hidden layer. But more importantly, each little neuron model was only linear. So you have just a bunch of linear combinations, and all you get out of that is I can solve linear problems. When you wanted to train something that was nonlinear, like you had a sigmoid threshold function, that gave us some extra power. So in 1989, we could use calculus and do, derivatives and stuff and do gradient descent in a much smoother way so that we could solve new problems that were nonlinear. That's really, really important. And that was a huge change, but that happened in 1989, a long time ago. So deep learning is still kind of small. And then in 2010, we got this stuff. Neural networks started doing things like winning at Go. And we had things where one machine would train itself by playing against itself, like different copies of itself, which is really cool. And they can do things that are tasks. Neural networks are amazing at really formal tasks. Like the Go thing seems super creative until you realize that Go is actually a pretty simple game in terms of the rules. And it's limited. So if we approach it with a deep neural network, it's not surprising that AlphaGo can actually make a lot of progress. Here's a real question about intelligence. If you can play Go, are you intelligent? Or do you also have to know something else? That's an easy question for me. You're not intelligent if you're just a Go machine. And so now in the quest towards general AI, we've got a long way to go. But we've made it some distance with neural networks. So what are these things anyway? Well, I sort of explained a little bit about how they work a minute ago. But they are inspired by the brain, only very loosely inspired. So down at the bottom we have we have a brain up here, we got a dog, and the dog comes in through your retina, and it gets some cones and rods, and those do edge detection, and then in V1 we get some simple shapes, and we start building things up in the visual cortex up to V2 and V4, and then out we come with faces and objects, and all of a sudden we see, oh look, it's a whole bunch of people wearing masks listening to me make shit up. And that's kind of cool that all happens in your brain. And so we're thinking, well, maybe we can do that in an artificial neural network. So we'll have some input that's a picture of a dog, and in the first layer of neurons we're going to do the simple stuff, and then the next layer is going to do some more stuff based on the results of the simple stuff, and so on. And if we pile up enough neurons, and we train it over millions of examples, dog, cat, wolf, dog, cat, whatever, a million times. Then at the end, it'll say something like 85% dog, 15% cat. Is that how you guys think? Hey, wow, good to meet you, 32%. No, we don't do that. That's not how we work. But that's how neural networks work. And the neuron models are incredibly simple. They just have axons. They don't even have dendrites. So it's just like, they're not very neurally. If you look at actual neurons and try to model those, you can build some more interesting models. And there's some work in that field that's getting somewhere cool. But we're going to focus on these really simple things that got all that. So one of the problems is there are lots and lots of models. Many different ones. And we can't really talk about the specifics of an exact model. Instead, when we do security analysis, if we want it to be useful, we need to build a generic model. And so one of the moves we made at Bibble was to just propose this generic model. Here's how deep neural networks kind of sort of work in 9 easy steps. You get some data, you do some crap to the data, you make some training sets, you have a learning algorithm, you train the thing up, you build a model, eventually you evaluate it and spit it out, and you get input from the real world and the thing that you spit out, which gives you an inference algorithm, and lo and behold, 85% dog, 15% cat. Does that make sense to everyone? So when you do this, this is an architecture analysis diagram. Because now we can think about each one of those things, either the processes, which are ovals, or the collections of stuff, which are rectangles, and we can think, if I were a bad attacker, what would I do in this stage of the neural network system? And that allows you to think through a risk management view and identify a whole bunch of risks. So we did that exercise. And we identified 78 risks. And I'm going to tell you about those that are associated with each of those components. First, a little bit of bitching. Since I'm an old guy, I get to do some bitching. I don't like the words that we use in security often. For example, I think that the field that I helped to invent should be called software security. And I really do not like to call it application security. No, 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 no. Here's why. Application security, the term came from network security people who were looking at the OSI stack and went, doobity, doobity, doobity. Oh, look, layer 7 is called the application layer. We better secure that one too. What? No. Did they not know that all their stuff, like every bit of gear, was made out of software? Come on! Software to me is like a very basic building block. Same with hardware. Hardware security is very important. A lot of people are working on that here too. So I like to call this field security of machine learning, or security engineering for machine learning, or something about machine learning and security smushed all together. A lot of people, especially at Microsoft, like to call this adversarial machine learning. Now, that's not a terrible thing, but it sort of implies that you have an attacker. And as all of you know, we don't really have to have an attacker around to build security risk into our system. We can completely screw up a system with no attackers around and then ship it, and then the attackers will show up, and then we're screwed. Just think about the SAP talk that we just heard. You know, later they're like, oh, maybe we'll hire these guys to poke some. Oh no, oh, that's a bad way to do it. It's really expensive too. It's like when you hire penetration testers to tell you your stuff's broken, and you're like, you know, now we have to fix it, and it's cheap to fix it after it's done. No, wait, that's backwards. It isn't cheap. Wait, why are we doing this again? Right, so adversarial machine learning doesn't make me happy. I want to call it machine learning security. I'll get off my whining. I'll stop whining about that. But I will tell you about some attacks. I don't really care about specific attacks on machine learning. We'll talk about some right now. But what I care about is risks that are based on those components that I showed you before. I want to focus our attention on looking at risks and thinking about those while you're building a system, not looking for this attack. Oh, I need to find this specific attack or that specific attack. Because there are too many attacks, and the bag of attacks is not that useful conceptually to think about. Anyway, if you really stand back from all the attacks we've seen so far and squint, here's a taxonomy that kind of works. It's really simple. It only has 6 boxes. One column involves manipulating stuff, and the other involves extracting stuff. When we manipulate data, we get things like poisoning attacks. When we manipulate input, we get adversarial examples. When we manipulate the model, we get a Trojan or backdooring. More about this later. I'm not going to talk about those specific attacks. Over here, when we do extraction, we can do it on the data, where we pull the data out of the model. Oh darn, we thought that was confidential, and then it's just sitting in the model and anybody can get it out? No way! Or input extraction. Hey, we know exactly what you put into that model because we are the model and we can tell you. Or model extraction. That's the best one yet. It cost OpenAI $12.5 million to build GPT-3. But if you use the right techniques, you can build a copy for way cheaper, which is kind of interesting. This is the way I think it's the best way to think about attacks, as just a few simple kingdoms of attacks. I would rather talk about risks, because we have to do better securing beyond the attack of the day. We can't just secure against adversarial examples. We have to secure against all future attacks we can think of. So we have to think through those risks while we're building something. So our work is about that. And it's more related to what I talked about this morning: reliability, robustness, all those software abilities, safety, all those things are all deeply related to security, because they're all properties of the system that we want. We want those system properties. And I believe that no system that's unreliable and fragile can ever be secure. I'll tell you about this example later on, but this is an example. This is an adversarial example. Another reason I don't like that nomenclature. Right, so let's talk about the risk analysis. We have 78 risks that we found. I'm not going to tell you about them all because that would be boring. I'm going to tell you about one risk for each of the components. So that's 9 plus a bonus risk, so that's 10. And then at the end of the talk, I'm going to tell you the top 5, which we're going to cover on our way to getting there. So from here on out, it's pretty easy sledding in this talk. We start with our raw data in the world. Data are essential to machine learning. What we're learning is we're making the machine be the data. We're changing the machine around using the data until the thing does what we want with the data. So the machine is the data. Does that make sense to everyone? This is very strange for those of us who used to build computer programs and the data was over there, and we had to sort of figure out, well, what if the data looks like it, whatever. This is, remember, we're doing the what, not the how, with lots of examples over millions of things. So if your data are screwed up, guess what happens to your machine that you build? Screwed up. So you have crappy data, you end up with a crappy machine. It's not too surprising that if you use, say, 4chan, 8chan, and Reddit text to train your model, you're going to end up with an asshole model. Seriously, just an asshole. And you don't really want your model to be an asshole, so don't train it up on that stuff. Now, that's an obvious case, but there are far less obvious cases than that. There's lots of raw data out there, and we can just get some, but if we get it and we train up a machine on it, we really should think about that before we do it. What's in that data? Do we really want that to be, learn about that? You teach your kids the stuff on 8chan, or whatever it is now, 32chan? Are they just moving up the, I don't know. So, because of this, if you have confidential data, like say stuff protected by GDPR, woohoo, everybody's favorite button to click, thanks Europe. If you have stuff protected by GDPR and you teach a neural network with all that GDPR protected data about individuals, plus you're supposed to forget some later, I don't know how that works, and you train it up into your model, is the model supposed to be protected by GDPR? I don't know. You know what? Nobody knows. There are lawyers or barristers or whatever they call them in the UK working on that right now. It's very, very interesting. No one is sure what the answer to that is. But if you have, let's say, super secret military data and you train up something for targeting, say, on tanks, and you have super classified imagery from space you're doing that with, and then you get done with the model, don't just give that model to the Russians. No, bad. Keep it, because it's got all the data inside it in a way that you can extract it. So confidential data in means the confidential data is in there. And there are many ways to get it out. There are many well-known extraction attacks. So that's one example of a risk. We identify, let's see on this thing, 13 risks, and that's one of them. Then we got to assemble the data. So data doesn't come in the right form to put in a DNA. We have to like mungify it. You know, mungification is a technical term that I'm sure you're all familiar with. So we mungify the data, and we do things like label it, and you know, we come up with some examples that we want to train it with, and we pay the people on the automatic turf to do that stuff for us. And you know, we have lots of people labeling stuff and teaching the machine what it really wants to know. That part of tagging and bagging stuff is a big deal, and it can be directly attacked. So if we do it wrong, the machine won't be able to generalize properly. If our data set is wrong and the examples are wrong, it's going to learn the wrong thing. I'll give you an example. So imagine a neural network that's supposed to learn the difference between dogs and wolves. And so you train it on a bunch of dog pictures and a bunch of wolf pictures, and you have a training corpus, then you have a checking corpus, and everything seems cool with the checking corpus, and then you ship it out in the world, and it doesn't work at all. And you go, well, why not? It seemed to work on our whole test set and everything, and it worked on our thing with wolves and dogs perfectly. It could discriminate. It was a great little classifier. Why doesn't it work? You know what? Turned out that a network in the line paper example learned that all pictures of wolves had a little bit of snow in them somewhere. And no pictures of dogs had any snow in them. So what it learned was, look for snow and say wolf. And that actually works for the training set and the test set, but out in the world, it doesn't, because if you have a picture of Fido on snow, it's going to say wolf, and Fido is like a Pekingese, little tiny dog. That makes it dumb. This can be much more serious, though. Like, think about COVID. We're trying to look at pictures of lungs and determine whether or not people have COVID. And it turns out that somebody did try to do that with training data, but the training data were screwed up because there was lots of training data from a pediatric hospital where there were kids involved, and it learned that kids have COVID. Because all the x-rays had COVID that were kids. And so if it ever saw a kid, it'd go, COVID. Like, no, that's my kid. That doesn't have COVID. COVID, gibbet. And if you can't explain how these things are working, that's what you get. You know, and some people are like, it's the magic machine. It always does the thing. We just do what it says. Follow the machine. And those of us, the rest of us, hacker people, are just like, follow the machine? Those things break all the time. They don't really work. What are you talking about? So we need to let them into some of that skepticism. Just because the algorithm says so doesn't mean you should do it. I mean, good God, what people do when they read on Facebook, they do these crazy things. That's bad. Those people are going to trust machine learning algorithms that are dumb. So that is one example of another one. Annotation out of 8 in data set assembly. Now, one of the tricky things that we have to do when we build these things is figure out what the training set should look like. So if we have the dog-wolf thing, we have to have enough pictures of dogs and enough pictures of wolves, and we have to have them skewed in certain ways. There is a lot of work that people put into building these data sets, especially the training sets. You can't just go out and get any old data, as the annotation stuff showed. So data get grouped into these 3 sets. And you know the advice about this goes something like, well, you know, you just train it until it's done. and then just check it with your evaluation thing, and if it passes that, that's good, and then you're good. You probably, we'll have some test things that it's never seen before, and then we'll ship it after that. And you're like, well, how many should I have? I don't know, just enough. Yeah. Well, what's the percentage of evaluation stuff for the testing stuff? I don't know, maybe 10%, 20%. Just try some, see what happens. Yeah, but how do I know when I should ship the thing if it's really working? Well, I'll just hold back some data. How much? Some. You think I'm kidding? That's how it really goes. So what happens in neural network land, for the most part, is people get these models and they just kind of screw around with them until they work. And then they write a paper about it. I'm not kidding. There are many papers that say, well, we set the parameter to 6. They say, empirically, which means we fucked around and found out 6 worked. But you can't really put that in the peer-reviewed paper. You say, empirically, we found 6. Did you try 7? No, because 6 worked. Yeah, but how about 4? Oh, I'm not sure, but 6 is the way. 6. This is, yeah. So when you say, well, how does the thing work? Well, lore says set it to 6 and then do it for a while. With that set, 10 or 15 is that work. So honestly, big problem. So one of the risks that we have at the data set level is that we use data that are intentionally manipulated by a bad person. Poisoned data. And it's pretty easy to poison data, so you can change the training set that the network gets. And in fact, some of these networks are so sensitive that the order of the training set matters. And you can change the behavior of the model according to the order of the same exact data set as some other guy. And get it to do what you want it to do. Ross Anderson and his people at Cambridge have been doing that stuff. It's really incredibly cool work. So, data poisoning is real, and that means you have to think a lot about the data that you're going to cram into this model. But mostly people are just busy trying to get more, and they're like, oh, there's some more over at Reddit land. There's some more, places you don't go on the internet. They go and crawl and shove it into a machine learning model. So poisoning is real. Online systems are a problem too. So once we've got a learning algorithm, what we usually do is we train the thing up, and then we get it where we want. We say evaluation's all fine, the test set works, we're good. We ship it, but we stop learning. We turn off the learning part where we're adjusting all the stuff in the middle millions of times. That is an offline system. That's what they mean by offline. They're using all of our words wrong. An online system is one that keeps on learning after you ship it. So you put it out there in the world and it's still learning. A good example of a still learning problem that led to some sort of crazy feedback loop was Google's translation mechanism, which was going out and looking for, translated stuff to run into its brain, and it kept on learning out there in the world, and it came across its own work. And it was like, wow, this is the best translation I've ever seen, because it made it itself. And then it crammed it, and it started doing insane things because it was believing itself. You don't really want that to happen. That's bad feedback. That's one example. Another example of an online version, who's heard of Tay in here? Tay was a Microsoft Twitter bot that Microsoft put on Twitter for about 15 seconds before it burned their fingers. And Tay was supposed to be on Twitter talking to other Twitter people and becoming what do they call it, a Twitter community, whatever, a bot on Twitter. And of course, as soon as Tay got on Twitter, everybody started to screw around with Tay, including bad people and trolls and misanthropes and, all the usual garbage people on Twitter. There are a lot of garbage people. So the garbage people made Tay become a garbage person immediately. Tay was so embarrassing that Microsoft was like, oh my God, it became a racist, turn it off! Look at what it said! Which was funny, but also not funny. It's funny, not funny. This is what happens to your uncle on Facebook, by the way. Your uncle's very much like Tay. So that's the sort of thing that happens out there in the world. Online is harder than offline. Offline's easier, but that's an example of a risk. There are 11 risks, so 9 other ones in that one. Right, so moving on, we have evaluation. This is kind of trying to figure out when's training done. Remember, you build the evaluation set by saying, that'd probably be a good one. Because no one's really sure how you do that. You just sort of do it. So you do it and it sort of works. And you say, I'm done. And you ask, how good is the trained model? We have this risk of overfitting, especially with enormous models. Imagine that you have such a big model that it has a big enough brain to store every single thing you ever showed it. It just memorizes it. You know what else we could call that? Lookup table. Lookup table, really good at the problem, but as soon as you get to the edge of your training set, it's like, I don't have any idea, man, I just look it up. Well, how about this tiny little 1 pixel difference? Nope, not in there, sorry. That's overfitting. And what we want the machine to do is generalize. We don't want it to memorize. When it memorizes, that's not what it's supposed to do. And that's a risk. And it's a risk that a lot of people that use these systems are unaware of. And now that we have bajillion node things, that can become quite a problem. Overfitting used to be something that was common in the 80s. We had much smaller networks. Then moving on, let's see what we got now. Inputs. This is pretty much the same as raw data in the world and going into data set assembly. So what input do we feed into the trained model? And where do we get that? It's very similar to the risks that go that way, but it's coming in at the end. And this is where things get really interesting. So I'm sure you've heard of adversarial examples in here. Who's heard of those? A few, yeah, a lot. About 60% of the people have heard of those. Adversarial examples are when you take a picture in a categorizer, say, and you're looking for cat or dog or 85% dog or whatever, and you put a little bit of a mask, change a few bits or pixel colors, pixel saturation sometimes, and the thing just completely falls off the wagon. Forgets. Like it just goes, I don't know, leopard, come on, man. And a person that looks at the same thing with the mask would say, that's the dog, it's a little bit screwed up, but it look, you know, and there are very bad examples of this, like put some tape on a stop sign and the wrong machine will go, oh, speed limit 45, cool. That's how Teslas work. I mean, the Tesla talk this morning was really cool, but why do all that shit? Why not just get out some tape? You know, or LiDAR, just like blind it with lasers. You ever do that? That's kind of fun. So, who would ever do that? Oh no, bad people doing the bad thing. So adversarial examples are the most commonly talked about thing. You've probably heard about the stop sign example. I think it's even in some museums in Germany from what I understand, because one of the people that was working on that at Michigan, or maybe it was Washington, got their PhD there, and then came back and is working in Fraunhofer. So that's interesting stuff. However, that's not all of the problems in neural networks. So when we think about risks, that's one of 78. Important to think about, an important one, but only one of 78. So if you just say, we're going to make sure our thing doesn't have adversarial examples, well, you're going to miss a lot of other stuff. Not only that, but there's some theory that was recently developed at the University of Virginia by a guy named Dave Evans that was published at Usenix and his students, PhD students, whose names I forget, I'm sorry. The work says, if you can solve the problem with backpropagation and generalize to the extent that you want, you will have to be susceptible to this adversarial example. You will have to be. On the other hand, if you don't generalize to the extent you want to solve a problem, then you won't have adversarial example problems, but you also won't do anything interesting from an ML perspective. Really very cool work to check out. So that means we have to live with adversarial examples. And let me tell you one other thing that bothers me about adversarial examples Anybody ever heard of malicious input in here? Like, oh, everybody? Right. That's just malicious input. Except for now we call it adversarial example because, that's got to be technical and scary and a lot of syllables. Right, but it's just malicious input. Moving on, we have our model, and we use these things, reuse them intentionally. Often it's expensive, like building GPT-3 costs $12.5 million. So you want to find a way to reuse it, and the most common way to reuse something is to have something mostly trained and use transfer, and then train it the rest of the way when you put it where you want it to be. So we have like maybe a circle finder, and we want to turn it into an oval finder. We want to build an oval finder, we start with a circle finder, because it already knows some stuff. Right? So this idea of reusing is extremely common for economic reasons in machine learning. But if you just willy-nilly reuse whatever and you have bad people putting Trojan functionality into your network, maybe it does something you didn't know, and maybe there's a way to tickle that with a special piece of input that'll make all tanks called cats from now on. Really? Like, how do you know? Did you train it? Nope. You just used that model? What? You remember when we used to just download code from wherever and there weren't even checksums? It wasn't even a cryptographic checksum. I mean, no checksum. It's just like, dude, here's some code. Cool, let me just eat that. Back in the BBS days, that's what we did. Because there was no integrity checking at all. Now we know better, and we're like, well, if you don't show me the MD5 hash, I'm not going to run it. Did you run it yourself? Okay, the bits are the same. Now, right, whatever. You know, now we have some integrity checks, but we don't have the same thing in neural network land yet. And there is Trojan functionality, and there are a lot of papers on that. So that's a risk. We're getting towards the end. Now we have our inference algorithm, and it does the thing. It takes the input, does the output, it does the thing. And you say, well, how does it work? It does the thing. It takes the input, and now the output comes out mostly right. It does the thing. Yeah, but how does it do that? Well, you know, thing it does. The thing. So often, we don't know. We don't know. It works. See, it works. We can test it. We do some testing and it still works, so we're just gonna ship it? Yeah, but how does it do that? There's a whole field called explainable AI that's about trying to explain how these things do what they do in terms that a person can understand. Because really the math is a little bit difficult when you have like a 1,000,000 dimensional space. 1,000,000? Like I'm pretty good at 3, but not 4. 4 involves time, that's a little too hard. 3, we can do 3, but 1,000,000, we can't really do 1,000,000. So how do you talk about how these things work? Attractors in a dynamical system? Really, we just don't know. Which feature is the feature that made that medical system decide that I have cancer? Oh, you know, one of those ones, we took the picture and we put it in there and you definitely have cancer because it says. Yeah, but why does it say? What did it notice? What did you notice? Aren't you a doctor? No, I just do what the machine learning thing says. And it says you have cancer. That sucks. Not so happy about that. We can't do it that way. And you know what's ironic? You don't have to explain how to people. Normals, they're just like, cool, I got it, the computer said so, okay. Like, these are the people that when they get a $400,000 water bill are like, oh my God, I can't believe I used that much water. And you just say, well, how much water do you think is on Earth? Because $400 million worth of water would be like an ocean-sized pile. And they're just like, well, I paid it anyway, as the computer says. I mean, it's sad but true. And those people are going to be like, the neural network said I can't have a bank loan, so I guess I don't get one. And we need to know why, especially if the why is the wrong why. Inscrutability is an issue. And inscrutability is the friend of the attacker. if people always think the network is right, and then you can make the network do the wrong thing when it's mostly right, except for when you tell it to be wrong, you win. Right? That's a new way to own a system. And then finally, we can just do an attacker in the middle attack on the output. After all, the whole thing is a big box and it squirts out the answer, and so you just change the answer on its way out. And because everybody trusts the magic AI, they think that's fine. So that's an example of a risk 2. So I've told you 9, and then there's one I want to do on the system risk, and this one's a little bit serious. So you've probably heard that we have issues with bias in machine learning, and we do. Think about it this way. Imagine that a bank has data going all the way back to 1948, 49, whenever the war ended, and they kept all their data from then on about who they gave a loan to. In the United States, that means a bunch of white guys giving a bunch of other white guys money until 1968 or so. And then we had a couple black guys, but mostly white guys getting white guys money. If you train a machine to make loan decisions on the historical data, it's going to make loan decisions like were made in the 50s. Have we not made any progress as a society since the 50s? Well, the Trump people sure as fuck haven't. But the rest of us have. Like, seriously. We're sorry, we knew we were stupid, but we didn't know we were that stupid. We are stupider, we're really stupid. I think it's television. And so this can happen also in situations like recidivism for prison, where you look at prisoners and whether or not they're going to do another crime, and you just look at the number of black people versus white people in prison in the United States, it's disproportionate all of the ways. And so all of the thing has to do is just go, black guy, oh yeah, put him back in there, he's not going to do another crime. It sucks. It's institutional. The institutions that we're putting into these automated systems are already doing the wrong thing, and now we're going to automate it and make it a magic solution. We cannot do that. We can't do that. So it's important that we think about the data that we're using, that it's not sexist and racist and misanthropic and doing the wrong thing that we're training a machine to do. It is up to us to stop that. And we can't just say, no face recognition. I mean, we can try. Good luck with that, But how are we going to do it? That's a good question. So we have some work to do. That's troopers' work right there. That kind of work. All right. In the last 2 seconds, I'm going to give you top 5 risks, and we're going to be done. Number 1, adversarial examples. I already explained them. School bus? Yeah. Pheasant, or is that a quail? Quail. Mayan temple. Yeah, everybody. Those masks in the middle are applied to the thing over here. So normal picture, mask, screwed up picture. You know what the neural network says? Leopard. Yeah, adversarial examples for the win. Data poisoning. If you put bad data into your machine, it will be a bad machine. Bad, turn off. Right, so poisoning is super important, and it's tricky. It requires special attention. Like, now, who got to touch that data before we took it over here? Oh, everyone on the internet? Really? Huh. I'm glad those are all nice people. Yeah. Online system manipulation. Do not make a TAE. When it keeps on learning, especially if you feed its tail to itself, it's going to be too easy to fix. And there, we already learned this lesson from intrusion detection. And intrusion detection uses an operational profile that's really clever. And if you're a good attacker, you can just move your profile over this way for a while, carry out the attack, and then move it back over here, and nobody ever notices. So you just slowly drift into attack land and back, and no one notices. This is something from long ago, and that's what's happening now. You know, online system manipulation is going to be a big thing to think about. Number 4, transfer learning. Transfer learning is a problem because of economics, and basically we want to reuse somebody else's work and just train it up a little bit, and we have some stuff to do. And so data transfer, you know, we might get a thing, somebody might take our system we intended as a hammer and misuse it as some other sort of tool, or a shoe as a hammer, or whatever. And you can't really anticipate as a person who grabs the machine what it was supposed to do, or describe exactly how it does what it does. So that's a huge risk. And in the field, everybody's borrowing everybody's work right now. And then we get right back where we started from. If you put secrets in your machine has the secrets in it. And you can get them back out. Attackers can get them back out. You might look at the machine and say, I don't see the secrets in there anywhere. It's just a bunch of neurons with numbers and stuff. The secrets are in there. And you can get them back out. So be careful what you put in the machine, because, you know, if you keep it to yourself, you're good. But if you share all your secrets, well, you don't have any secrets anymore. And that is an introduction to machine learning security. And I'm done.